Well, first of all, I'd like to thank Ayush for the kind invitation, and it's a pleasure and honor to be back here. I was in New Jersey last fall, and I visited Rutgers a number of times. Lots of friends here. Um, so today, well, the title is Questions about AI and Mathematics. So um, really, I've kind of flipped the narrative. Usually, um, speaker will be like teaching you guys about some stuff, and I thought this would be a learning opportunity. I mean, I'm really here because I'm good friends with Ayush, and there are a lot of AI experts in this room, and I'm more of a person who wants to get to know AI experts and learn about AI and all that. So kind of your average Joe mathematician, and so maybe this will give you practice in communicating with those people that don't know much about AI. So I just have to figure out how to, oh, okay. Um, So I guess one question right away is, what does it mean to do mathematics? And probably this has been discussed very much. There's well-known papers like by Thurston on proof in progress in mathematics. And so, and I assume that what it means to do mathematics will be changing, right, as AI um, develops. And so perhaps one maybe have a rather inclusive definition of doing mathematics. Okay, so so first of all, I want to reiterate that the purpose of the talk is to learn from you, and rather than simply tell you what I think, to invite discussion and to think about things together. And so for me, what I'm really interested in is how can AI, in particular chatbots, help us do mathematics? So I think of it as black boxes, and I have no idea what's going behind all the theory behind it. But I like thinking about mathematics. I'm not particularly good at doing research, for example, but I do like writing books and all that. Although I find it very painful, actually. And one thing I wanted to mention is that in the past, I have a lot of great co-authors and all that. So I do all the janitorial works, like compile the index and et cetera, et cetera. And I think that's one of the benefits of AI is it can do a lot of the janitorial work. Like you kind of I don't know if that's the right word, outsource it to that. So you can kind of think more structurally about projects and books and research. And so, kind of thinking about what is doing mathematics, you can think about exploring the known or the unknown. Like if you're a student reading a book, it could be very exciting to just read some basic book, even though it's well-known material. Again, learning mathematics, and that's what we hope our undergraduate students want to do, right? So instead of just getting a good grade and all that, and the graduate students we assume that's what they're here for. And we like thinking about mathematics, understanding mathematics, knowing mathematics, questioning mathematics, appreciating mathematics, and so on. So kind of immersing ourselves in mathematics. And I guess probably one of our first exposures to mathematics is through books. Right? So just on a personal note, this is um, kind of like the first book I remember like being really excited about. So I just want to uh, share with you this. And so William S. Massey comes into this talk later, actually. Uh, but we'll get to that in a little bit. Okay, there's a lot of pictures and it's like cutting and pasting topology and surfaces and all that with triangles and all that. Just was very beautiful. So when I was an undergraduate, I thought that was just so incredible. And the thing is, I probably got the book maybe just months after it came out. Actually, that shows you how old I am. Like, I think it's published in 77. Is that right? Or about that time. Okay, so I did mention, I like to work on books with co-authors. And one question is, how does AI help us with books? And so um, this is something I want to explore. So I haven't, most of what I've done with AI and books is use it to like, oh, should I put a Oxford comma here? Should I dot this I? Should I cross that T and all that? Um, and then I kind of thought, well, maybe I'm not really using AI to the maximal benefit. Like if I do that, there may be better things, and that's something I want to explore this year and kind of like see like can we use it to kind of like figure out the structure of our book and all that. And of course, there's a lot of janitorial work, like can it, you know, compose the index? Can it kind of find all, references and all that, create a bibliography? And usually those things would be very tedious. And so it's kind of amazing. And also have some other thoughts about maybe books and AI. So one, can it help us write books? And that's what we've been chatting a little bit about. And can it help us read books? So here's a kind of a random thought is like maybe AI will start to develop, and this is more a question for the room, is like let's say you're a student, undergraduate student, and you're reading Baby Rudin for your analysis class, and typically I don't know what percent, maybe 90% of the students like will be really struggling with that, and then the question is, can you just use AI, in the future to kind of create a version of Rudin that's exactly at the level of the student. So you just kind of expand on it and all that and fill in more details. And somehow by the person using the student using the chatbot kind of tell the AI enough about themselves, or maybe because they've been using it for so long, already knows that kind of create another version of Rudin where it can find, oh, this is really easy to read and a lot of fun instead of struggling. So in that sense, I almost wondering if books are passe. I should stop writing books and all that. They shouldn't be something static, really, whether they can be kind of developing and all that. So we could have like 1,000 or a million, oh, maybe there are a million people that want to read Rooted, but different versions of it. Each take, and that's probably a general thought that people have, right? That AI could be a personal tutor, right? And so, but you can maybe expand on that idea. And so, what movie is this from? Since we're math nerds, or science nerds, it's Neo. Looking at Know Thyself in Latin, apparently. Okay, so that's kind of that's kind of the feeling I have is when you use AI, it's like to help your weaknesses. So you have to be really honest with yourself about what do I suck at? And of course there's what you're good at, but it's really complementing. Like the best thing is if it can be um to really work. And I remember I was once in the I think it was a science center and with my advisor, and he said, you should show your weakness. And kind of that really resonated with me. And so kind of if that's kind of one thing nice about AI, that it can kind of patch up your weaknesses, and probably more so. Should I move this scroll bar to the top or something like?
Thanks.
Yeah, okay. And okay, so there's that idea. I don't know if Socratic dialogue's the right word or words, but we do have conversations, right? So that's kind of happens naturally. So the question is like, how do we have these conversations? Well, one thing that's really cool is that basically chatbots do whatever you tell them to do, right? So it's just like you have well, a genius, and you're just able to pick their brain and all that, and they will actually be like doing all the difficult stuff for you, like if you're working on a paper or book. And that's kind of crazy, that idea. And so, as I mentioned, like we typically, because it's kind of, maybe we're at the cusp of AGI, maybe, right? So they're typically stronger than our weaknesses, but maybe not as strong as our strengths, right? Especially if we're just like specializing in something. And they say, well, like, okay, there's this little corner of math that I might know a little bit more than AI does at this moment, although in 2 months the story might be different. Um, so there's a question which might be relevant pretty soon, or well, or sometime in the future, is what will happen when chatbots are stronger than our strengths? I don't know if anyone has the answer to that. A lot of people.
My opinion is that they're much better than I am personally at cooking.
Yeah.
So I would defer to a reliable chat. Tracking on something.
Yeah. I do the same. Yes. They're wonderful that way. And now, this is probably not what you're expecting, right? I do not have the answer to your question, and I will not try to answer that question. Yes.
But how do you feel about like this idea that chatbots can only really get as strong as the strongest mathematicians because it's trained on, papers and books written by the strongest mathematicians, and then do you see a clear path in which chatbots can sort of move beyond without having to train on material written by, the strongest?
Oh, yeah, I don't know if I'm qualified to answer. I know that
Sure.
better than anyone else, but I never kind of believe in the originality of mathematicians in some sense. I mean, all ideas kind of come from earlier ideas and all that. And if you find the connections and all that, it seems like um, it seems like they think very well horizontally. And that's probably one strength. And so maybe creativity is somewhat of an illusion, who knows? That maybe they'll will appear to be very creative.
But we haven't
Better
seen
than, pardon?
but we haven't seen evidence to that effect yet.
Well, it just keeps progressing. We
Sure.
just have to wait and see,
Yeah.
right? And nobody knows. But I mean, I wouldn't be surprised, like, if it just
Yeah.
becomes like quite amazing, but I'm certainly not qualified to answer. But thinking about horizontally, I remember my youngest daughter, like in grade school, they asked, like, this is not the question, but, why is a dog like an airplane? And so they're trying and I never understood that. It's like, isn't this a little bit too early to, like, they're trying to get the kids to think horizontally, but it's so superficial and all that. And, education is trying to encourage that, think outside the box. But somehow you kind of have to know a certain subject, very well, then another one, then you can start doing like that. But that's what maybe chatbots would be good at, right? Because they know everything, and then they can find the connections. But
I also think that it's AIs are not only trained on the outputs of structural competitions, they can reinforcement learning. We know that,
Sure.
they're better at doing that playing chess for reinforcement.
That's true.
Yeah,
you
yeah,
know,
yeah.
fundamental.
Yeah, so that just makes the case stronger, right? Okay, so I decided to pivot from that question and instead ask what we might do before that happens. So that's another thing. It's not like this is probably a very in history. It's a very transitional period in society and in the world in science and all that. Maybe we shouldn't think too hard about this. We should just do what we enjoy. But this is a bit dramatic. Okay, so maybe you should not say maximally adaptive, but maybe we should try to be flexible, right? Because if AI is changing very fast, how we will use it will change probably very fast too, right? Along with how it's changing. Like at this moment, you say, okay, I can do these tasks, but maybe like 6 months from now, well, I can do something very different, and it'll be cool to adapt. Okay. And oh, we should really try to make the most out of the best AI tools that we have available to us, right? And kind of think about that. Again, this is kind of I have no right to give such advice. I don't know any better than anyone else, but it's just kind of something that sounds like would be a good idea. Okay, now, and you could say this, right? Just like all rushing in to, because it's changing and like, like we should just like jump in and there's a lot to be said for this. And that's kind of the way I think about working on hard problems is that, I figure like, okay, this hard problem, like out of 1,000, 999 will fail. But nature is like that. You need those thousand of people to work on that one person to succeed. And it's fine to be one of the 999. That's what I keep telling myself. So if I don't get any work done, that's fine. Yeah. So I just also rush in. Um, but here's a quote. Fortune is a goddess that favors the brave. And I guess this is a Greek quote. I don't know if it's written exactly, but this was actually written by a Greek mathematician, and it was written by Demetrius Christodoulou. So in the notice of the AMS, there is a memorial article for Richard Hamilton of Ricci well fame. And so in that article, should be a direct quote. Yeah, that was a direct quote. And so what happens is that I forgot what year it was. Yeah, maybe about 14 years ago or so, something like that. Richard Hamilton and Demetrius Christodoulou were awarded the Shaw Prize, and they shared that. And Richard Hamilton is very hard to get a hold of. And apparently at that time he was in Hawaii, and Demetrius Christodoulou got hold of his email and to let him know that he had received the Shaw Prize. And that's in the email back, that's what Richard Hamilton's reply was. Okay, so we certainly have a choice to make. And we choose to go down this road. And I think maybe that's one of the takeaways for me that I'm thinking about for this talk is that it's basically, there's no one fixed advice. It's just each one of us decides for ourselves, like, how we find this interesting and all that. And then just on a personal note, it's a few years ago, my youngest daughter, Isabel, she gave me the book Be Water, My Friend, The Teacher of Bruce Lee. It's by his daughter, Shannon Lee, and all that. So I kind of think of that as kind of going along with being flexible and adaptive, right, in the age of AI. Okay, so that's just some general thoughts about AI and mathematics, and there are more questions there than answers. And so in this part, I thought I would give just some simple examples you using AI and mathematics. It's a very superficial use of AI. But on the other hand, AI is just like a really smart partner, right? You can work with. Like you can just have to remind yourselves, like, I should use a chatbot to do a lot of things, that typically might take more time. Okay, so this relates to a paper that Mike Friedman, Henry Shin, Yujia Zhang, and I published, and it's about self-similar singularity models for Ricci flow and dimension 4. So we're in the realm of smooth manifolds, right? Like you have surfaces, like two-dimensional spheres, tori, double-hole tori, and surface of higher genus, for example. And even those are orientable. You can even have non-orientable surfaces like the projective plane or the Klein bottle, and etc. And higher connected sums of projected planes. And that was all described in Massey's book, right? That I just showed in the earlier slide. And so that's Ricci flow is pretty well understood in dimension 3. So there's this Hamilton-Perlman proof of the Poincare conjecture and something much more general, which is Thurston's imagization conjecture. And then there was further works, especially by, for example, Zeeman Brendle proved the conjecture of Perlman. Richard Bandler proved the conjecture of Perlman too, another conjecture. So in his paper, he had a few conjectures. And then there's other things like Bandler and Kleiner proved the generalized Smale conjecture using Ricci flow. And there's other works by like Kleiner and Lott that were related to that. And so it's kind of kept developing. So one thing that's very interesting is Ricci flow in higher dimension. And so this particular paper, we're looking at a four-dimensional manifold, and four-dimensional manifolds are very complex. So four manifolds in the topological category, say simply connected, are extremely hard to analyze, but there's a very simple answer given by Mike Friedman about their classification. So that's for topological manifolds. But if you look at smooth manifolds, then you could have, for example, two smooth manifolds that are homeomorphic. Their underlying topological manifolds are homeomorphic, but they're not diffeomorphic. So those become really quite a complicated zoo structures there. And that and that direction, I would say, started with Simon Donaldson, and then he developed that direction within other people, and then kind of some significant simplification came from the Seiberg-Witten equations. In any case, in Ricci flow, what you can do is you take a four-dimensional manifold, you put a geometry on it, and you form it by a heat equation, the Ricci flow. And then what you see is the geometry starts to smoothly change and all that. And the idea is that it's trying to get better and better. You get a nicer and nicer geometry on your four-dimensional manifold. But what can happen is, and this already happens in dimension 3, you could have singularities forming, right? Things could start to the curvature, which is one of the main invariants describing the geometry, could get larger and larger, and things could kind of, in some sense, break. And so singularity models are simply when you look at this heat type equation, the Ricci flow, and when things start to break, you start to zoom in and you see if something really, really nice happens. And in dimension 3, that is true. So there's a classification of singularity models due to Hamilton, Perlman, and Brendel. And so one could study singularity models, and one could actually look at self-similar singularity models, namely ones that don't move under Ricci flow. So it's a very paradoxical thing that you can have these singularity models that under it itself, it's a limit of Ricci flows under microscopes whose magnifications go to infinity. And it's a solution to Ricci flow, and under Ricci flow, it doesn't move at all. And so that's a thing we studied. And so maybe to characterize the idea there, it uses kind of a geometric topological argument to prove an analytic estimate. So we show a curvature bound for these things. So these things are non-compact. So, like R4, right? Non-compact. The non-compact four-dimensional manifold, and the curvature is like a function on that manifold. So it's not compact, even though it's smooth, it could go off to infinity and all that. And so it was kind of a contradiction argument where you want to show the curvature stays bounded. And so you can think of that as an analytic estimate. And then we use some geometric ideas like index theorems, like, for example, Chern-Gauss-Bonnet formula and Hertzberg signature theorem. And well, essentially, it's kind of with boundaries, so the signature eta invariant comes in there too. And then it becomes kind of it morphs into like a topological argument where we look at the boundaries of these. One actually looks at embedded four manifolds in a bigger form. And their boundaries will be actually connected in spherical space forms. And all that. So we kind of look at whether the argument is by contradiction, and we get a certain situation like this where we have a compact four manifold inside this non-compact four manifold, and it keeps repeating itself. So like you could have a million copies or any unbounded number of disjoint copies of this, and one wants to understand why this cannot happen to prove our curvature estimate. And then it becomes something about showing something about the H1 of the spherical space form. And that kind of morphs into homological algebra, and then finally like finite abelian group theory. Okay, so it kind of goes on this interesting trajectory. Okay, so we'll just mention one aspect of it is that so we have these we want to show that the singularity model, its underlying smooth manifold is a smooth four manifold. We want to show it has bounded curvature, and we finally reduced it to showing that the first homology group of a certain embedded three manifold which bounds a connected compact four manifold in the bigger four manifold is a direct sum of finite abelian, well, direct sum of a finite abelian group with itself. So sometimes this is called a direct double. So we want to show this is true. And that's what caused us a little bit of problem. And well, Max is here, right? So this is very apt that he's the one that pointed out an error. So we really have to thank him, right? We would not have a complete proof without him pointing that out. So then we posted, so then the story goes about 6 months later, we posted a correction to his paper. So That was posted on archive in May of 2025, so we thought we fixed it. But the story continues. There was actually a remaining gap in our correction paper. And so we're kind of, the referee pointed some questions while this is not clear, and we realized that we still had work to do. And so earlier this year, we finished repairing the proof. And so I want to discuss a little bit, just in very general terms, how the repair came about. And I'll just look back at a few excerpts from our conversations, and you can find out there wasn't, we're letting ChatGPT do most of the work in terms of certain isolated tasks. So I guess one key thing is to give it enough context. So of course we inputted, well, we might have inputted the original paper, but we certainly inputted our correction paper, and then the referee report, and then our revisions based on the referee report. So then we just asked it simply like, can you list all errors? Tell us what the correction would be, and for our revised paper. Okay, but the short story is that with the help of ChatGPT and through Socratic dialogue with it, we believe that we essentially have addressed all the referee's concerns, so that we could kind of read through very clearly line by line, and it all makes sense, and it's all correct as far as we know. Okay, so that was kind of a very short story about that. What I wanted to say a little bit more about is what we did next. So we said, okay, ChatGPT is very helpful for assisting us and making sure things are correct, and sometimes filling in details, etc., and kind of polishing a paper. And so there is a somewhat tangentially it's related, but it's a somewhat different question. So about 6 years ago, I asked Mike Friedman a question, and then actually very quickly he solved the question in a 2-page handwritten note. Okay. So we thought, well, since ChatGPT is really helpful for our previous correction paper, that we finished like in March, the correction paper. And then, well, why not try to revisit this idea and see what it can do with this note? Okay, so the first thing we asked is, ask ChatGPT, could it verify the correctness, fill in details, and perhaps even generalize the result? Why not? Right? Just see, like, it's just like throwing a dart at a wall and hoping it sticks somewhere. Okay, well, what happened is we were surprised by that. There's quite a dialogue and iterating improvements using ChatGPT. We turned the note into a longer paper, much longer paper. Part of that is filling in details. Part of that is a generalization. Okay, so, well, I happened to save the original note. So this is the note from 6 years ago, and this is the proof of a special case, and I'll kind of maybe too small to read, but its note is actually in 2 pages. Okay, so what we did is we typed up the note. I mean, maybe now we just have to scan it in. You don't even need to type it up. And summarize, I asked ChatGPT to summarize the math in this paper and like put in some background, like, okay, let's just pretend we can, well, it is a paper, but pretend like we're gonna write it or actually just write it as an actual paper. So let's put in some definition. So it uses like notion of twisted Euler class because it's going to be about two plane, rank 2 vector bundles over RP2, the real projective plane. And 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 so randomly we asked, just out of curiosity, is there a natural generalization of this definition to, okay, so that was me asking. I'm sure Mike knows the answer. He would not ask a silly question like what I put in there. But okay, is there a natural generalization of this definition of twisted Euler class for non-orientable, supposed non-orientable surface? Okay, so it says yes, there is. And so okay, so we had like 3 questions. So I'll just give the replies to the person third. And it just says what the main theorem is. That suppose we have a closed orientable smooth Bohr manifold. So how does might arise the Ricci flow? Well, you're flowing Ricci flow for a metric on a closed Bohr manifold. So you're always doing that. The singularity model is like when you blow up, because if you use a microscope whose magnification factor goes off infinity, distance scales get larger and larger, and the limit could be non-compact, right? But you start with something originally. So then the question is, can we bound how many pairwise disjoint smooth embedded projection planes that can occur? Okay, and we want to put a condition that has a normal bundle with twisted Euler class of absolute value greater than 2. And the reason is there's this Berenice embedding of RP2 into S4 or R4. And that has twisted Euler class 2. Okay, and if you look at the unit circle bundle over that is actually S3 mod Q8, where Q8 is kind of like group of order 8 based on the quaternions. You take plus or minus 1, plus or minus I, plus or minus J, plus or minus K, right? It's 8 elements and all of that. And by the way, if you Bielanize that, I think you get Z2, QX72, which is a direct double. Okay, so that was the result that yes, there is a bound, right? Our result is that there is a bound. So you can't have arbitrary many disjoint copies RD2 whose twisted Euler class satisfies this absolute value of it is greater than 2. And then the third question was a simple question about whether twisted Euler class worked or other non-orientable surfaces. And the answer is yes. And then it's remarkably minimal, like what we ask GPT. And that's kind of the cool thing about AI is like you almost don't have to ask anything. It does this kind of wonderful thing sometimes, and it's just in the right place at the right time. I'm trying to like train it on Ricci flow. Like, okay, here's the whole history of something like Harnack estimates, and here's all these, these are ideas and blah blah blah, and then it's kind of leading up to this. And you think like, okay, I really prepared it really well. Like, tell me something new and all that. Like, where should I? And it doesn't know what to do. So it's kind of. It just somehow, if it's in the right place at the right time, it can do things. So it's not like, well, like I prepared it better and therefore I should give a better answer. That's not necessarily
So
true.
you tried to train it?
Well,
Like you
like I throw in like lots of books, tech files, lots of books, tech files,
into this context.
into its kind of like project source files, like lots of paper, like it. And then explain the whole historical development of a certain direction, and then think of, tell what I know about this, what I think about things, and it's like still kind of flailing, just like really, it's like, but like what gives me hope is that, well, there's this other context where it's a lot easier. I just simply, threw in a couple of papers and just asked like the simplest question, and it like seemed to do very well. Yeah.
Also, just for context, this is the pro version and not just the thinking version. Sorry.
Yeah. So everything is a mixture, like of pro, but the main thing is like for simple things, you just like an instant or thinking mode. It could be like standard, but then anything serious, you just like keep on going pro. So, and another thing that kind of skipping ahead is that you keep bashing it for the same thing. Like let's say you want to refine a lemma, you say, okay, here's the lemma. Can you make sure this is right? And it always nitpicks something. It's like, okay, I don't like this, and you should explain this, and then okay, and then you feed the answer back into it. And you just kind of relentless that way. You just keep telling it, like, okay, like make this 100% correct. And you're just like bored and you kind of say like, like act like a barracuda, like a bat out of hell, just referring to like 1970s rock songs by Heart and Meatloaf and all that. I mean, things like that. Imagine you're the greatest referee in the world, and just because you're bored, like, whenever you say something like that, it's not going to matter. It's going to do its best, like that. And so you just keep bashing it, and eventually, just like anything in life, eventually it gets bored and says, this is 100% correct. And then you check it and all that, and you decide. And often, more than not, in a lot of cases, it actually works. And so I would call it maybe convergence. You just keep on bashing. And that would be a great thing to automate. I think that's, like we had discussed before, like, just automate this process because it's really, you're not thinking about it. You're just telling it, just keep going back and forth. And so, yeah, we just, okay, it's positive and it will nitpick. It'll say, oh, there's something wrong. And it's like the kind of something that like to an expert like Mike, it's like, this is obvious. It'll just say, oh, okay, there's an error here. But no, it's just like you didn't put in more details that was obvious to him and all that. But in another sense, that's actually very good for exposition because like if we think, well, later maybe part of the audience will be in reach flow, then they wouldn't know this area, like certain aspects of algebraic topology or more algebraic stuff that well. So having more details is better. And so chatbots can be very helpful for exposition. So when you say, oh, okay, there are several serious issues, it's kind of like aggrandizing things. Like sometimes it's right, like there might be, a significant issue somewhere, but other times it'll be just like, okay, that wasn't really as big a deal as it said. Okay, so it came up with the following. So this is the generalization. So instead of having just like our RP, RP2 with a fixed normal bundle embedded, unbound number of times, it says, well, just generalize it where you could just have a bunch of different non-orientable surfaces and a bunch of different, possible normal bundles, right, with different twisted Euler numbers. And then the idea is now going back to Massey, this goes kind of full circle to that he showed that this is the normal bundle of the embedded non-orientable surface, that's the Euler number. And he showed that this is less than twice times non-orientable genus of the surface. And he proved that. And the idea is that, well, when that's not true, right, if that's positive, that will actually accumulate, right? And you can't have too much because like it has to be bounded by some fixed constant. And so in a special case, like if you had a particular normal bundle for a particular non-normal surface, it's positive, and you have a certain positive number here, and if you had unbounded number, you get a contradiction. You'd be summing the same number unbounded times and saying that's bounded depending only on the ambient or manifold. And this is kind of the generalization that came up. And then the rest of it was just kind of going lemma by lemma, getting each lemma to converge like that. And once you get each lemma, it's okay, like throw in abstract introduction. What else do we need? Like, okay, now here's the whole paper, and then like make this perfect, and then, okay, here's the whole paper again, here's what you said. And then finally, like, crazy stuff can happen, right? So, okay, so, oh, it's saying like, okay, here's the proof of lemma 11, and it didn't like, my gradient had a certain proof, and it didn't like it, and it did some really weird detours according to him. And it kept on insisting on that. And you would just like put in both versions, and it always preferred its own version. And then Mike would have to explain more and more what he meant, like the things that are obvious to him. And then finally it came around, okay, it's happy with Mike's version, which was much better. And so things like that. So some limitations are kind of what it knows. Like if it doesn't know something an expert doesn't know, it'll do weird things just to make it perfect, like that. And so that's some of the limitations. Okay, so that just kind of describes what I mentioned earlier, like you check lemma by lemma, so very rudimentary. Then after you get each lemma to converge, then you just try to get the whole paper to converge. Okay, then what's going on now is wondering if we could like synthesize the two results, this kind of Euler excess result and other direct double result, and that it's not clear. So that's kind of one thing we're wondering about right now. But here's a kind of a conjecture, one conjecture that we think might be true. So we'll look at a compact format, or let's call it W this time, with the connected with boundary, and then it's another compact format with N. Maybe it's closed, so the compact format of N might say not have boundary. And then if you have an unbounded number of embeddings of that four manifold into that closed, say, closed four manifold N, then the reason you have is that because it actually embeds in R4. So that would be a possible conjecture. And that's not known. Right? I think that would be pretty interesting. Okay, so now to the last part of the talk is just basically about trust. So kind of when we think about how we use AI and what we can do with it is really based on trust, right? If it's giving us good answers, then we try to do more. So the scale of what we do gets larger and larger depending on how much we trust it or and all that, or what ways we use it. And well, okay, here's another movie. Oh, Neo back again. This time it's kind of the counterpoint. This evil twin, Agent Smith, and he talks about purpose, and that's so that's the question: is what is our purpose? Well, one possible view is that we're by using AI, by trusting AI, by developing AI, we're not defeating our purpose, but rather redefining it, right? Like what we think is what should our purpose be in life? So what is that purpose? Another big question. Well, that perhaps is left in the eye of the beholder. And that's a question for each one of us to answer for themselves. Okay, so I think that's all I had to say for today. Thank you very much.
So you mentioned putting together bibliographies for writing books. Yeah, have you used SciSpace inside of ChatGPT?
I have. Is that
So with the GPTs, it has 400 million journal pages, has access to them. You can specifically ask, please give references that discuss this particular work, and you can put in LaTeX, and it will export a bibliography in BigText.
Oh, cool. Yeah, it's called SciSpace.
SciSpace, SCI.
Oh, cool. definitely, I'll look into that.
It's, they call one of the GPTs, so if you have the Pro model, you can search the GPTs and just, click size space and it'll open a chat window and you can just use chat. So you can use natural language in a query and ask for, to export the bibliography in chat.
That's cool. Thank you for letting me know, because we haven't really started using the AI for the books that systematically, extensively yet. And that's something hopefully, so this would be very helpful.
So this, it's the best tool I've seen on the market for around, telling you which papers discuss topics of a certain topic.
Nice. Cool, thanks.
Is it ever hallucinate? I haven't actually seen hallucination. It seems to be, I mean, it has access to, has subscriptions to journals.
Yeah, it seems to be much better in general, like about hallucinating references. Before, it's like it creates these crazy references. It mixed different mathematicians, like, okay, they work in the same field, we'll put them together, and then they'll like mix papers and they create a completely new paper.
It's just a, plausible probabilistic answer. Simple. But it's size space actually
Yeah, definitely.
goes directly to the journals.
Well, thank you.
I have a question for you. So last week I was at this meeting at in San Francisco. And one of the questions people asked one another is, suppose AI gets to the point where you just say, here's a theorem I think might be true or might be provable. Can you tell me if you can prove it? It just says, yeah, I can prove it, here's the proof. Or if it says, nobody can prove this, you won't prove it either, neither will I. Humanity, we're not entitled to this here. Would you still do math?
I would. I just want to know if something is true. Like, for example, I don't want to have necessarily anything to do with the proof of the Lawton-Mace conjecture, but I just want to know what is true. It's like, I think I know that Fermat's last theorem is true, right? And I'm just happy knowing that without knowing anything about the proof. And so I like.
You get even more joy, I assume, out of knowing the proof too.
Yeah,
Just
I
that
just
it's
like
right.
love doing that.
If an oracle tells me the Riemann hypothesis is true, I'm not satisfied. I want to know why.
Yeah,
How
yeah.
did you prove it?
But
But if it explains it to me and I'm not the one who discovered it, I still get a great deal of joy out of doing that. Whereas a small number of people, so Jacob Zimmerman was one of the people who was driving this question and saying, if all I do is I ask the AI for proofs of things, then I will stop being a mathematician.
oh, really?
The vast majority of us said, no, we'll still have it. I just want to know, I want to know the proof.
Yeah. I
I
mean,
still enjoy.
I'm with you on that for
Yeah.
sure. I'm a math groupie, so I just, I just want to be around math and all that. This is more,
Yeah.
And so I don't have to be the discoverer of something. And just immerse myself in it, whatever way possible. Like if I can't understand proof of Fermat's law theorem, I'm just happy knowing that it's true. That there's this Hanayama-Shimura conjecture, and that it's much more structure in that than just the statement of Fermat's last theorem. That sounds very exciting to me. I think that kind of.
That's like,
I think kind of misses the point, like the scenario. I mean, if you just have an oracle that's telling you the answer, and you don't understand any of the answer.
let's say it explains it to you in a way that you do understand, if it can come up with a proof. If it can't come up with a proof, then basically there's no chance that you will either.
Fair enough. But
Suppose
the explanation part of it, that's fine. But the point of being able to ask the next question that's meaningful really requires understanding. Right? I mean, there's
You
lots.
don't think you can tell it, ask the next most meaningful question.
I don't think so. I mean,
I also don't think so, but I can't say why not.
I mean, think about, I don't know about you, but oftentimes when I start working on a problem, right, I don't, it takes a long time to figure out what I'm really asking. Right? You have to kind of go down a bunch of different paths to realize that, oh, well, that's not really what I care about, right? There really is, even getting to the point of being able to say, okay, I want to prove a theorem about this. Is a hard process.
Yeah.
So it's a chicken and egg sort of thing. If we can't, unless we understand what we're doing, we aren't going to get asked questions. And if we're just asking blind questions, and getting blind and getting answers, even if they're correct.
But the questions we're asking are for a reason. We're trying to find a pattern, you know.
Right.
Why can't it also ask questions? Ask the kinds of questions we ask.
It probably could, but I think this, well, okay,
Hypothetical, right?
hypothetical, but I think that, it's really kind of pointless to develop a AI that mimics the human brain. I mean, we already have, there's a you, and there's a me. We don't need to make an absolute digital twin of ourselves. It's just a waste. I mean, I think these things are gonna go down a path where they organize mathematical thoughts very differently from us. And then there's gonna be this whole issue of translating what they're doing into something that we understand, and we appreciate the answers, but actually care about. And that's the human aspect.
And I would add to that, that the purpose is the understanding, it's not the answer. Because the answer doesn't matter all that much in your intent. But I wanted to ask you a follow-up question. Do you believe in that world? Do you believe the AI when it tells you we can't prove it?
You don't have to believe it, you can try to prove it. You can tell you we can't do it, but in practice,
And
no human being.
if it tells you that you can't do it, would you still try to do it?
If you tell you something is unsolvable.
No, then you won't be able to find a solution. It's not that there is no solution, but no.
We still got lots of people squaring the circle.